You can allow all the participants the once once again post the YouTube link in the group as well as the meeting link in the WhatsApp group and Telegram.
Sir, tell me, sir.
Once again post the meeting link in group WhatsApp group.
Sir, your voice is 2 times. Please check for echo.
Hello? Now?
Now good, sir. Now good.
Fine. Please post the group link in WhatsApp group. One second.
Hello. Welcome all the participants. The session will be starting in 5 minutes.
Hello.
Hello.
Good morning, sir.
Hi, good morning. Good morning. Good morning, Dr. Virendra. Yeah. So, shall I? I cannot hear you. I cannot hear you.
Yes, sir. Yes, sir. We are just about to start.
Okay.
Good morning, Sachin sir. Good morning and welcome, sir.
Yeah. Good morning.
Sir.
Yes, please.
See, start the session, Gautam.
Good morning, one and all. Myself, A. Gautami Naidu, once again welcoming you to the second day of our 3D FDP program, Emerging Trends in Electronics and Computer Engineering. I request Dr. Virendra Singh sir to introduce our speaker of the session, Dr. Sachin Kumar Srivatsav Garu, Assistant Professor IIT Roorkee, to the participants.
Yes, ma'am. Thank you. With great pleasure, I would like to welcome Dr. Sachin Srivatsav, Assistant Professor, IIT Roorkee. He has completed PhD from IIT Delhi in 2012 in the physics domain. Before joining IIT Roorkee, he has a very diverse and persisting background in the field of science and technology. Sir has done postdoctorate in Nanyang Technology University and Ben Gurion University, Israel. He's being started research associate in IIT Delhi as well as former scientist CSIO Chandigarh. So the research area of Dr. Sachin Srivatsav includes plasmonics and enhanced sensor configuration, enhanced optical phenomena-based sensing, SCRS, SEF, EOT, SCIRA, ESP, LSP, coupling-based sensor, nanophotonics, nanostructure, optical configuration, optical sensors, biosensor for water, food and clinical diagnostics, fiber optic integrated sensor, fiber optic plasmonic sensor, light matter interaction, strong weak coupling application to sensing. So we can see a lot of interdisciplinary areas are being in under a research interest of sir. So various project sir is associated with from DST, IIT, MHRD, like nano sculptured thin film based enhanced plasmonic phenomena and their application for clinical diagnostic and water sensing. So basically, SAR belongs to this plasmonics. It's a very quickly developing subject that combines fundamental research and application ranging from areas such as physics to engineering, chemistry, biology, medicine, food science, and environmental science. So before wasting even a second, let me hand over to sir. And the topic for today's lecture is plasmonic fundamentals to application. Sir, please, I request you to start just.
Please unmute yourself, sir. Sachin, sir.
Oh, thank you for letting me know. Okay,
Yeah.
first
Yes.
of all, I would like to thank Dr. Virendra Singh and Dr. Shiv Prasad for inviting me to this FDP. As introduced, I am Sachin Kumar Srivastava from IIT Roorkee. Currently, I hold a position of faculty in Department of Physics, as well as a joint faculty position in the Center for Photonics. And can you please allow me to share my screen actually?
Sultan.
Sir, give
Sure,
the
sir.
permission.
Sure, sir. Sure, sir.
You can share, sir.
Okay, I can share now. Yeah, just a minute. Yeah, I hope you can see the screen now.
Visible, sir.
Yes, sir.
Visible.
Visible.
Yeah. Okay, so in this, so yeah, I have a joint faculty position in the Center for Photonics and Quantum Communication Technology in IIT Roorkee. Okay, this is a newly established center, and hopefully it will be doing some cutting edge research as well as courses on quantum communication and photonics. In IIT Roorkee, basically, I am working on plasmonics and its applications primarily on sensors. So whenever I'm talking about applications, it is mostly on sensor. This is one of the photos from my experimental setup. You can see that light is coming from here, and then there is a prism, and on the top of prism there are some kind of waves which are traveling. So I will discuss this, and then when I develop the subject, you will understand it more. If you have any questions, you raise your hand at the immediately, okay, and you ask me, because this is a FDP, and I hope that everyone should understand it. So let us first try to see start from the application, that is from the sensors part, and then I will develop the subject, and then I will tell you what we are doing and how it can be done, used for applications. Okay. So when I said applications and in particular sensors, so basically sensor is a device which measures the change in one physical parameter in terms of the magnitude of a second different parameter, which can be measured more conveniently and perhaps more accurately. What it means? It means that I want to measure something in terms of something else. Okay, I want to measure a parameter in terms of some other parameter. For example, I have given here 5 photos. You can see that this is a thermometer. So if you take this example of the thermometer, what it measures is actually temperature, but which parameter is measured is actually the length of this mercury or alcohol column. So by measuring the change in the length of this column of mercury, you can say how much change in temperature occurred. This is a conventional glucometer where you put a drop of blood here, and then it tells you how much is the glucose concentration there. Okay, but if you see clearly, what it does actually is that it measures some current between the electrodes or voltage across the electrodes, and that reading is converted into the glucose concentration. Now this is another kind of this is another sensor that is somehow it's not working. I don't know. Can you see it? Because my laser pointer is not working, it seems.
Okay, sir. Okay, sir.
Just a minute. Previously it was working, now it is not working. This is working. Laser pointer should be working, but I can't see it working. Okay, I hope you can see my cursor. Can you see my cursor moving? Can someone?
Yes, sir. Yes, sir. Yes,
Okay.
sir. Yes, sir.
So laser pointer is somehow fixed, but this is moving. So another one is pregnancy test kit. You can
Okay,
see that ladies know it, that you put a drop of urine and it will tell if the lady is pregnant or not. Okay. This is an infectious disease biosensor. You can say that it is like people can go and cough in here, and then it will tell if there is some disease or not. And this is old time coal miners biosensor. This kind of bird coal miners used to take to the coal mines, and if there was some unpleasant situation, let us say some leakage of some gas like methane or something, then it will start crying, and then they will know that okay, it is time to evacuate. If you closely look at these sensors, right, this thermometer and glucometer, they say that there is a change in temperature or there is change in glucose concentration, and they will say how much change occurred. Okay, so it is quantitative sensor. It tells you that that there is a quantitative change. However, this pregnancy test kit or disease biosensor or coal miners biosensor, these are qualitative sensors. I mean, pregnancy test kit can tell you if the lady is pregnant or not, but it cannot tell you that how many weeks of pregnancy is there. Like you had this COVID test, it was like COVID positive or COVID negative. It didn't say that you are infected with 1,000 viruses or 10,000 viruses or something like that. Okay. Similarly, like coal miners biosensor, if there is leakage of methane gas, it will start crying, but it cannot tell you that how much leakage is there. So both kind of sensors are important. Sometimes, you know, you have seen during the COVID that it is like yes or no kind of sensor is also very important. And at the same time, qualitative sensors are also very important. And they are everywhere. They are everywhere. Just a minute. Let me try again, because the cursor is not moving. I'm not happy. Okay, now it's moving. You can see that we are polluting almost everything, be it air, water, or food. We are putting lots of pesticides here, and then you know it remains there on the food, and then we become victim of various diseases. Okay, various diseases. You know, if you can grow fish in this kind of water, you will have some contaminations there, and if you eat it, you will become victim of these things. So this is one of the things. This is an old data. It was a prediction from 2017-14 or so, and it shows that the annual market growth of biosensors is like about $2 billion per annum. But let me tell you that after the COVID, it has already crossed like 50 million or something, more than that. So the market has huge potential, and that's why it's very important that sensors. Every country should be self-dependent on sensors, and then only, you know, it's a billion dollar market. It's a $1 billion market. Now let me try to tell you what we are doing in our lab. But before that, one more thing I want to tell, that what are the components of a biosensor. So you have a sensor surface where you put generally a biorecognition element or bioreceptor, and then if there are some places left, you want to fill this place so that nothing can go and bind on the sensor surface. And when this binding takes place, it will lead to change in either pH or refractive index or mass or any other thing, which will lead to change in some measurable signal, like change in optical signal, electrical signal, acoustic signal, or dimensions, for example, the length in case of thermometer. Okay, and then this signal is sent to the detector. So some binding took place here on the sensor surface, and it led to change in the signal, and this signal is detected. So this complete thing makes a sensor. Okay, so transducer is a part of a biosensor. Okay, transducer, detector, all these are parts of biosensor. So people many times confuse between a sensor and detector. So please remember the detector is just part of sensor. Okay, it's like a subset of sensor. I have a lab in IIT Roorkee which is named as Applied Plasmonics and Photonics Lab, and we are working on various sensors based on these techniques. One of these is fiber optic plasmonic sensors, where we do make sensors on optical fibers either on the tips or in the middle. What we do is that we take a part of the cladding and then we do coatings here which specifically detects some molecules, and light comes from this side, goes from this side, and then if you have a binding you get a dip. Now if some other binding happens, the dip position changes. So by measuring the shift you can see how much change in the analyte occurred. Then we have a book also here, and if someone wants to learn more, he or she can purchase this book, and it tells a lot about the binding methodologies and everything. एक मीटिंग में हूँ, नहीं, thank you. Then another thing is extraordinary transmission. That is another method where we have nano-structured slit arrays. You know, this is sub-wavelength arrays. This has lots of good physics here, and still light can pass through because of plasmons, and we are using it for sensor applications. We are making prism-based SPR system. I showed you a figure there in the beginning, and we are using it for detection of, let's say, hepatitis A virus or listeria, this kind of. And then we are doing imaging also. So you can image the surface plasmons, like this is a resonance dip, and then we are using different kinds of beams to see that how can we improve the performance of the sensor. And when we are using something called plasmon enhanced spectroscopies, where we use finger-like structures of silver or gold, which are we are calling it nano sculptured thin films. Okay, these are finger-like structures, and they give enhanced Raman and enhanced fluorescence signals. I will discuss one of the cases of bacteria detection and glycated hemoglobin detection. And then we couple the plasmons of thin films, which I was discussing here, and these are like nanoparticle-like structures. So then we make nano cavities here. So you can see that the field can be enhanced like 10 to the power 5 times or so. And when you put a molecule here, this is called a hotspot. You can increase the Raman signal like 10 to the power 10 times. Okay. So under suitable conditions, once you achieve this, you have enhanced signal. So again, it is plasmon enhanced spectroscopy only. And then very recently, in collaboration with CSIO Chandigarh, we started working on this spatial beams, which are basal beams on tip of optical fiber, and you can trap nanoparticles using this. So you can see that nanoparticles are trapped within the rings, and then you can enhance the signal and make a sensor out of this. We work on plasmonic metasurfaces. Metasurfaces are something which are very interesting and very hot and new topic. I will discuss some recent results from our lab here. This is purely theoretical result, which I will discuss. And then we are using machine learning and deep learning in our sensors. Okay, here, and then another thing is we are doing lossy mode resonance sensor. So this is also another theoretical study, but the benefit here is that you don't need to use metal and still you can enhance the sensor. So these are some of the things which we are working on. Okay, but let us try to understand the fundamentals of plasmons and plasmonics, and then we move to the applications. Okay. So outline of my talk will be something like this. I will first introduce what are plasmons and localized and extended plasmons, and then we will see some applications like plasmon enhanced spectroscopy based E. coli detection, HbA1c detection, and plasmonic metasurfaces. And finally, I will summarize my talk. So plasmons are quanta of longitudinal oscillations of free electrons in metal. Okay. It's like to synonymous to plasma because it has a large number of electrons are involved. Okay, so you can think it like this. You have water, okay, and you drop a pebble. Once you drop a pebble, what you see? You see that waves move like this, like you see it here, okay? Is that okay? You can see that, right?
Yes, sir.
Yeah. So if you try to picturize this condition, what happens that suppose you drop the pebble and immediately it went down, immediately. So if you are sitting inside the water, what you will see is that waves are coming like this. What are these? These are longitudinal waves, compression, rare fraction, compression, rare fraction, compression, rare fraction. Okay. If you put a piece of paper on top of this wave here, traveling, let us say you put a piece of paper, what you will see? You will see that it is oscillating like this, and at the same time it is coming out slowly. So inside, you have a longitudinal wave, and on the top, it is partly longitudinal and partly transverse. So this kind of wave is called plasma oscillation. So if I have a, let us say, a thick piece of metal, let us say this is a thick piece of metal here. In this, if I can somehow create this kind of oscillation, this will be longitudinal oscillation. Okay. But I'm talking about something which is electromagnetic wave. Electromagnetic waves are transverse in nature. So we can excite electromagnetic surface plasmons, not plasmons, bulk plasmons. Okay. So we can excite plasmons, and that is on surface, because this is transverse wave. Electromagnetic wave is transverse wave. So that's why we talk about surface plasmons. So surface plasmons are now oscillations of free electrons at the surface. So you have essentially a metal dielectric interface, and on the surface you have a wave which travels, and while it travels, after going to a certain distance, it will die out. This kind of wave is called surface plasmon wave. So it travels along the interface, and its field decays both in this medium and this medium. You can imagine it like this. You have a wave, you have a person who is amputated. Let us say one arm is small and one arm is big, and it is walking on this wall. So it's like this. वो दोनों हाथ फैला के चल रहा है इस पे. He's walking like this, but one arm is small, one arm is, let us say, cut. Because in metal you have losses, so the field decays very rapidly. Okay, but it is decays immediately, and here it decays to a large distance. You go large distances there. That kind of wave it is, and it is purely transverse magnetic. So let me tell you what is transverse magnetic and what is transverse electric. So transverse magnetic or p-polarized light is light where the magnetic field component is transverse to the plane of incidence. So if this is if you light comes like this and reflects like this, you and make a plane like this, where reflected light and incident light is lying in the plane. Then if the magnetic field is pointing out of the plane, then it is transverse magnetic. And if electric field is lying out of the plane, then it is S polarized or P polarized. That is the magnetic field will be inside the plane. Magnetic field will be in the plane of incidence. And here in p polarization, electric field will be in the plane of polarization. So if you see electric field is parallel to the plane of incidence, then it is p polarized or TM polarized. And if electric field is perpendicular to the plane of incidence, then it is called S polarized or TE polarized. Okay. So now, if I have S polarized light incident, then what will happen? The electric field is pointing out of the plane. So electric field is out of the plane. So we will not have polarization charges. No polarization charges can be created, because if you have difference in electric field here at this interface, only then you can create polarization charges. So that's why you cannot excite surface plasmas using S polarized light. Now let us see what happens to TE and TM mode. If you write the wave equation for TE mode, the wave equation given by this equation, where this electric field is EY, and in case of transverse magnetic mode, it is HY. Okay. So if you want to write down the exponentially decaying solutions, the EY and HY are given by this. Now you write down the solution for TM mode. So you write down the electric and magnetic field components in both the interfaces, this media, and then you apply the boundary condition. So if you apply the boundary condition, and what you will see is that you will arrive to this condition. So this is also positive, KZ1 is positive, KZ2 is positive. So when it will become 0? When epsilon 1 and epsilon 2 are having opposite sign. And this will be happening only when one of the materials is metal. So it is very important that one of the materials should be metal, silver or gold, and other materials should be dielectric for excitation of surface plasma. However, if you have transverse electric mode, you will have this condition. So this is not equal to 0 because this is metal and this is dielectric. So minus sign, this will not be equal to 0. So that means this equal to 0. So EY equal to 0 means there is no mode for transverse electric. Only transverse magnetic mode can excite surface plasma. Okay. Any confusion till now? Anyone? Any question? So you can see that it is like a wave like this. So you have a metal and you have a dielectric, and if the electric field lies in the plane of incidence, this is the plane. So you can see that electric field is in the plane, same plane. Then it will excite surface plasma. If the electric field is out of the plane, let us say it is cross or dot, it is going out of the plane, then it will not excite surface plasma. And when the surface plasmas are excited, it will go up to certain distance and then die out. Why? Because the wave vector of surface plasma is given by this expression, where K surface plasma wave vector is K naught, which is the wave vector of light incident in the dielectric medium from free space, and epsilon m is the dielectric function of metal. Epsilon is the S is the dielectric function of the dielectric medium. So if you have epsilon m is actually has complex nature, real and imaginary part. So if you put epsilon m is equal to epsilon m1 plus I epsilon m2, you will have kx1 like this and kx2 like this. So kx is actually not real but a complex wave vector. Okay, so real wave vector means if you have a wave e to power I omega t minus kx, this kind of wave you have, and now you want to have kx, actually k dot r, this is a wave, and k is now real and imaginary both. So if you can take real part out, imaginary part will be like I and I multiplied, it will become -1, and then this will add to decay part. So this real part is responsible for the oscillatory nature, like this wave is traveling up to infinity, but this part will lead to decay. So the propagation length is given by, because of this thing only, right? And you can see that for gold, I have this simulated at two different wavelengths. I have calculated for gold air interface, the wave will go up to 10 micrometer, and then it will die out, or 15 micrometer and it will die out. For silver air interface, because the electric losses are small for silver, it can go up to 50 micron. You can make a device of 50 micron length, and that is perfectly fine. Such a small device you can make. You can make miniature devices. Now the field also, I told you that field also decays rapidly if you go away. So that is called penetration depth. So you can see that when you have, let us say, for example, gold and water. So for metal, it decays very rapidly. It decays very rapidly from here to here. It's called penetration depth. And it goes up to, let us say, 250 nanometers or 300 nanometers for silver. If you increase the wavelength, from 540 to 633, you can see that this is hardly changing. It is like 26 again here, almost same, but here it changes. So you can control the penetration depth by controlling the wavelength of light which is incident. Okay. What is the benefit? So benefit is like this. So you have a wave which is decaying like this here, and you can change the wavelength, let us say, from blue to red. So it will become like this. It will increase the penetration depth. So if you want to sense, let us say, a molecule which is small, if you want to make a sense a molecule which is small, you can use a blue one. But if you want to sense a molecule which is, let us say, large, like this molecule, if a molecule is this big, then you cannot use the blue one, because it will give you only half of the information. It will not give you the complete information. You can see that the penetration depth is unto here. So half of the molecule will not be probed by the laser light. That's why you have to change the wavelength. So this is called penetration depth engineering, or penetration depth engineering. You can engineer the penetration depth according to the molecule you are going to sense. Okay, this is something which one has to do. Now excitation of surface plasma. So I can see here, for example, there are lots of people here, and now Gautami says that, okay, I have silver and I am wearing silver on my earring here, and then I have a ring also here. So I can excite surface plasma, because now this is silver and then there is air, I shine light on it, and then I can excite surface plasma. This, someone can think that, okay, this is possible. But let me tell you that it is not that straightforward. You cannot excite surface plasmons so easily. Why? Because of this condition. So suppose you have a metal dielectric interface. You have a metal dielectric interface here. It supports this kind of wave. So if you solve the Maxwell's equation like I solved there, the wave vector of surface plasma is given by this expression. And the wave vector of light which is traveling from here is given by this expression. So you can see that if you have, let us say, frequency omega, for this frequency, the wave vector of light is k, while the wave vector of surface plasma is ksp. So there is a gap in momentum. So there is a change, so there is a phase mismatch. So even if light falls on this interface, you cannot excite surface plasma. You cannot. So we have to increase the wave vector so that it goes here. It goes from here to here. How we do that? We make it very thin. We put a dielectric layer, let us say high index prism, and then we incident light from this side. So there will be total internal reflection. Light will go like this, and this light will interact with this interface. So this red light line now moved to orange line. Okay, from here to here. So you keep on changing the angle, and there will be some angle where this line will be exactly intersecting this line, and then you will have k equal to ksp. So this is the condition for surface plasmon resonance. So what will happen? You are shining light from this side, you are changing the angle, and you are measuring the reflected light intensity or power, and you keep on changing this value of theta, and there will be some value of theta when there will be exactly matching this thing, and then all the light will be exciting surface plasmons, and you will have a dip in the reflected light. All the light which is incident here will excite surface plasmons, and in the reflected light there will be no power. So this is called surface plasmon resonance. Now you change the refractive index of this medium in the middle. Okay, in this medium, let us say you change it from N1 to N2, then this curve, the black curve, moved to now green curve. So what you have to do, you have to change this theta again, so that from orange it comes to blue, from A to B. Okay, so you moved from N1 to N2, you have to change theta from theta 1 to theta 2 to again have resonance, so that there is again it intersects at B. So you can see that you moved from theta 1 to theta, N1 to N2, the curve moved from theta 1 to theta 2. Some person can say that I'm not using, I don't want to change theta, and I want to change wavelength. So you can use a white light, and then it goes from lambda 1 to lambda 2, because the frequency of light changing, which is exciting surface plasma. So it's called, that one is called angular interrogation. This is called spectral interrogation. So by measuring the change in lambda, you can measure the change in refractive index. This is the basic principle of surface plasmon resonance based sensors. Basic principle. Okay. There are other methods, because this distance is like 200-300 nanometers. It is very difficult to maintain 200 nanometer gap. So what people do is they directly coat this metal film on the prism, and the surface plasmons are excited on this side. This is called Crashman configuration. This is the most popular configuration used for excitation of surface plasmons. This is commercially available also. Other method to excite surface plasmons is grating. So you shine light here, and because of the diffraction orders, there was a phase mismatch here. I have shown you that there was a phase mismatch which you wanted to achieve by using a prism. That you can use grating also to achieve the phase mismatch. So light will be incident, and the light will be reflected in various orders, and that order will go missing, which gets used to excite surface plasmons at this interface. Okay. There is one more beautiful physics. I will discuss that also, but remember this, that a rough surface, you have a rough surface here, you made a rough surface like grating, and then you can couple light to excite surface plasmons to this, and then you can simply replace the prism by using the core of optical fiber, and it will do the same job like exciting surface plasmons in Crashman configuration. The advantage is that it becomes then very small, and there is no risk of spark or fire, because this is purely light, and you can do online measurement. I am sitting in this room, I can do sensing throughout my city using optical fiber. So you can do remote sensing, you can make multiple channels, and you can do multiple channel sensing. That are certain advantages of it. That is all about propagating surface plasma. There is one more thing which happens, and that is the field enhancement. So you can see that the field can be enhanced about 10 to the power 2 times, about 100 times enhancement. When this is simulation result. What it means is that you excite surface plasmons, all the light is enhanced in the it's like concentrated near the metal film, about 100 times enhanced. So if you place a molecule, then you can enhance the Raman signal. Now there is a question by Akshaya that what are other materials used for plasmon other than silver and gold. So as I told you that there are few things one has to consider other materials than silver and gold. One thing is that people have to understand that the material should have a negative value of epsilon. That is one thing, negative value of epsilon. Okay, and second thing is that if you can bring down the losses to a small number, then it will be more beneficial, because then you can propagate to a long distance. So now people are using titanium nitride also. Some people are using indium tin oxide also in other dimensions. Now people have integrated graphene also at higher wavelengths in terahertz regime if they want to excite surface plasmons. So people are trying now semiconductors also, because semiconductors, you make a semiconductor device, you can do modulations and you can excite surface plasmons also, that will enhance the properties. So light chips now, which which are the future of photonic chips, which are the future of computer processors and all this, there they are trying to make this kind of thing where you can use light, you can send the information at the speed of light, at the same time you can use it with electronics and so on and so forth. So that is where people are going through. Okay, so this is all about propagating surface plasmons. Now so that is a film of thin metal film of silver or gold, and light can propagate to few microns, let us say 50 micron or so. But if you make a nanoparticle itself, if you make a nanoparticles which is much smaller than the wavelength of light, let us say metal nanoparticle like 50 nanometer, I am standing with 500 nanometer wavelength and this is 50 nanometer. What will happen? It shows different colors. And what are these different colors? These are different colors because of different kind of plasmons. So if someone wants to solve mathematically how to do it, it's given in J.D. Jackson. What you have to do is that you write the Laplace equation, and this is very small, so you apply quasi-static approximation. What is this? This means that you assume that this nanoparticle feels a uniform electric field. In electric field is like this, somewhere small, somewhere large, but you can assume that the particle is so small that it is feeling almost uniform electric field, and you solve the Maxwell's equations for uniform electric field, or Laplace equation here in this place, because you want to know the field, and before knowing the field, what you know is the potential. So calculate the potential inside and outside the sphere, and then you take gradient to know the electric field, and you apply the azimuthal symmetry conditions in terms of Legendre polynomials. It becomes very easy. Okay, you solve for this and you arrive to this condition. Okay, and you can see that here, if you have this equal to this, denominator will become equal to 0, close to 0. And when this condition arises, this is called Frulich condition or resonance condition, the polarizability will shoot up. That means the electric field will shoot up. Electric field is a function of polarizability. So electric field will shoot up. So you can see that it becomes like a dipole here. Okay. And because of the dipole, you have enhanced electric field in the vicinity. So now there you were getting like 100 times enhancement in field. Here you will get like 1000 times enhancement in the field. Okay. And now if you place a molecule here, let us say near this plasmonic meta structure or molecule, you will feel enhanced field. This molecule will feel like 100 times, 1000 times enhanced electromagnetic field. So the Raman signal or fluorescence signal or any kind of signal will get enhanced. And let us quickly go to the applications part. So Raman spectroscopy, you know that you excite the molecule and it comes to the same wavelength range. This is called Rayleigh scattering, but very small portion of this will have smaller or larger wavelength. So there will be a slight shift in the wavelength of the light which is scattered. It's called Raman Stokes or anti-Stokes signals. And this small shift here, this is a fingerprint of molecular bonds and crystalline structure. Okay, because there are different kind of vibrations, and these different vibrations of different bonds will give different Raman structures. So if you can measure the Raman spectrum, you can assess the Raman spectrum from some molecule that will tell you that this is the particular molecule which is giving the Raman signal. But the problem is that out of 1 crore photons, only one gets Raman scattered. It's a very weak phenomenon. You may understand how good experimentalist Raman was, that using sunlight he could make this experiment. Okay, then there was no laser at that time. With laser you have larger power, so you have larger number of photons. But what people saw, that if you bring the molecule near a rough metallic surface, plasmonic surface, you can enhance the Raman signal. And how you enhance the Raman signal? You bring the molecule here, you shine the light, so the molecule will feel the light of the laser and the field of this plasmonic metasurface. I told you that plasmonic field is very high, 10 to the power 3 times or so. So if you calculate the plasmonic enhancement factor, it is like 10 to the power e to the power 4 times enhancement in the field. But the problem is that this is a highly localized phenomenon. You increase the value of D, it will very rapidly decrease. Okay. So because of this only, you have 10 to the power 5 to 10 to the power 9 times enhancement. So 10 to the power 5 to 10 to the power 9, what it means? It means that I am calculating the enhancement factor per molecule. So suppose I am getting the 100 molecules absorbed on the film, okay, and I am measuring the Raman signal, then I divide it, Raman signal, with number of molecules. So that means the search signal per molecule divided by bulk Raman signal per molecule, and that will give you the enhancement factor. So whenever I am saying 10 to the power 6 times enhancement, 10 to the power 8 times enhancement, that means I am talking about essentially about field enhancement per molecule, not field enhancement. Actually, it is the intensity enhancement or power enhancement per molecule. So you can see that people have made different kind of structures, and you can achieve a high enhancement. We are making something like this, nano sculptured things, which are rod-like structures. I already told you, and they are prepared using something called glancing angle deposition, where you put the substrate at a glancing angle, and the metal flux comes like this, and you keep on rotating it, and you can make a tilt. So what happens actually, that initial phase, it makes nucleation sites, and this adds as a because this is a tilt, okay, like flux is coming like this. So whenever there is this, so this will act as a shadow region. So whenever molecule comes here, next molecule will come here. In the middle, there won't be any molecule, any AG particle coming here. So this way you create column-like structures. In the middle, there is no coating happening. Okay. So this way you create column-like structure. You can make a pre-template, and then the film grows over the template. You can make a rotation and rocker motion, and then you will get helix or something. So by this you can create large scale, and you don't need E-beam lithography or FIB or some complicated method. You can very easily use simple evaporation technique and make nano rod like structures. Okay, nano rod like structures. We have used it for detection of E. coli bacteria. So what we are doing here is that you have this film, and we attach viruses of T4 bacteriophage, which is very specifically binding to E. coli bacteria. You can see that E. coli bacteria are here. So light from laser comes like this, and then I have a filter here, so that clean laser light comes like this, and then light which is getting scattered from here, it's sent this side. Okay, and then I put a long pass filter so that it cuts the laser light which is achieved here, and only the Raman signal goes to the spectrometer. So we make different concentrations of bacteria in PBS actually. So you can see that it is like 150 cells of bacteria. This is called colony forming unit, that is cells. So 150 bacteria in 1 ml, and I am taking only 10 microliter, that is about 1.5 bacteria, like roughly 1 bacteria, till 1 bacteria per 10 microliter I am going. Okay. So what people do generally, they put the bacterial plates, and then they grow it overnight, and then they count the colony CFQs, and then they say that this is the bacteria and this is the concentration. But here we can see from the Raman spectra itself that you can tell in 10-minute time what is, and of course in 10 microliter volume, you can tell what are the bacterial concentrations. So that is very effective. And this is very, very sensitive only to E. coli. For other kind of bacteria, I used CV026, P. dietrificans, aeruginosa, and you can see that it doesn't show any change in the Raman signal. But for two different kinds of E. coli, it shows some changes. Okay, so that is how it can be used for sensing of bacteria. Okay, we used it for enhancing the fluorescence also, because 10 to the power 3 times enhanced field. So what we saw, that if you have simple fluorescence of silver nanoclusters, you can see nanoclusters also show fluorescence. Okay, and not only that, if you have carbon quantum dots, they also show fluorescence. I think this was this study was, purely accidental. You make silver and silver starts giving fluorescence. How? Because it becomes silver oxide. So they made silver quantum dots, and they never thought that, who thinks that silver gives fluorescence? I have silver ring, it doesn't give any fluorescence. But you make a quantum dot and it starts fluorescing. That is interesting. So we made this nanorod like structure and it was giving fluorescence. So I was wondering why it's giving fluorescence. Then I studied back and I found that, okay, probably it is getting oxidized, and because of this oxidized layer, you get fluorescence. And what is more advantage? You have plasmons here. So plasmons are enhancing the field of the same film 10 to the power 3 times to 10 to the power 4 times enhancement. I don't have to do anything. Don't have to do anything. I have to just make, controlled oxidation of this. Controlled oxidation. So that a very thin layer of this silver film becomes oxidized and it starts giving enhanced fluorescence. That's why we call it intrinsic fluorescence from STF. I don't need to use any fluorescent molecule and it itself gives fluorescence. So that is, I can use it as a fluorescence based sensor and I don't need to use any fluorophore. So it's called label free fluorescence sensor. It's a very interesting study. What I am doing is that I made a custom setup where light is coming from this side, and then I put my sensor chip here, and from the same setup I am using it for camera and I am sending this signal to spectrometer. So from the same micro spot I am doing microscopy and spectroscopy. Okay, so here you can see that I am getting the enhancement fluorescence signal, okay, from this surface, and about 30% porosity of this I am getting enhanced signal. So I am using this as a this thing, optimum film. Now I took X-ray photoelectron spectroscopy analysis, and then you can see that there are, of course, it's getting oxidized. So you can see that there are peaks of oxygen and carbon. Okay, apart from silver. Now I did etching for 10 nanometer using argon, and these peaks disappear. So it means that only up to 10 nanometer there is controlled oxidation, and after that there is no oxygen or carbon. So there is no fluorescence after that. And then I made a sensor for glycated hemoglobin. What is glycated hemoglobin? If a person is diabetic, what happens actually that the amount of glucose increases in the blood and then it attaches to the hemoglobin. Everyone actually, in all of us, some molecules of glucose attached to hemoglobin, that is called glycated hemoglobin or glycosylated hemoglobin. We call HbA1c. And since the lifespan of red blood cells is for 3 months, you can have a constant level of HbA1c for 3 months. So that is more reliable parameter for detection of diabetes. If I eat 200 grams of jalebi this morning, in 2 hours my sugar level will be high. Okay, that is not reliable. Okay, but this is reliable. This will not change immediately. For 3 months it is constant. So if someone is diabetic, it will be always high for 3 months. Okay, so I made a sensor using HbA1c antibody on this, and then I detected for various concentrations. This looks a bit weird, but I have translated the concentration of glycated hemoglobin in blood directly in this form, and you can see that when there is HbA1c, there is a decrease in the fluorescence signal, while for simply hemoglobin there is no change in signal. So that is the beauty. And I told you that I am taking the image also from the same spot. So this is the image of the sensor chip. So I am changing the concentration, I am taking the images also. I am taking the spectra and I am taking the image. And then I am processing this image also. And then from the gray counts also, it's showing the same kind of behavior. You see that the blue curve is correspond to the images and the black curve corresponds to this spectra. They are both showing the same kind of behavior. So this is how we make a sensor. Now let us quickly go to a meta surface. Meta surface is a surface, but only thing is that we engineer the surface. So suppose there is, like, I have silver nanoparticles or silver structure or gold structures, and I place them in such a fashion that it behaves totally differently. Okay, totally differently. I can control the wavelength which will pass through, which will block, and how it behaves, the phase of the wave, and everything we can do. So that is the beauty. So it's a very small structures and placed in such a fashion that it will give some other kind of behavior. Okay. For example, here this bucket kind of structure, this is a meta surface, and you can see that there are different kinds of peaks. Okay, and they used it for sensing, so sensitivity was like this. Then there is another kind of meta surface where they have created this grating like structure, and then they are trying this. Then there is slit kind of structure, then their sensitivity is like this. So they are making these kind of sensors. What we made is like this. You have one metal nanoslit array, and then other is like this. So it's like this. You can see the finger and the opening and the finger and the opening and so on. And then I have another one, and then I put it that way. That opening of this upper one will be closed by the lower one, and so on and so forth. Okay. And so it is like completely blocking the light. I have only gap of only 10 to 25 nanometer here, 25 nanometer gap. And you can see the light can leak through it. There is no opening actually. This opening of this is blocked by this, and still light can go through. And that we have shown theoretically that even if we start covering the upper one, covering the upper one, the closing it, only let us say like this or this, up to 90% I have closed, and still I am getting up to 90% I am getting like 60% transmittance. So you can see light can go through like this. Light can go through like this, even if I closed it. And then we used it for sensing applications, because it's plasmons only. You can see that the field is in this direction, and on the edges it is like this. You can see that electric discharge happens. This kind of thing is happening here in plasmons, and it's very beautiful. And you can see that light can funnel through it because of that only. And then if you change the refractive index of the medium surrounding this, you can use it for sensing applications. So sensitivity is like 1435. Here you can see that it was like 281, 275, 180. So we are getting like more than 5 times, 6 times enhanced, like 1500 nanometer sensitivity. So let me summarize my talk. I have discussed the basics of sensors and why they are important and why. And then I have discussed both kind of plasmons, extended surface plasmon or propagating surface plasmons, and then localized surface plasmons. And then I told you that plasmons can be used for the enhancement of spectroscopic signal to few orders of magnitude, and thereby enhance the biosensors. As an example, I showed you sensors based on surface enhanced Raman spectroscopy and surface enhanced fluorescence. And then I introduced you meta surfaces and shown that it can tune light by optimization, and hence can be used to develop highly sensitive biosensors. I wish to acknowledge funding from different funding agencies. I was lucky enough to get good funding from almost everywhere. We Inspire, IIT Roorkee, MOE, Ministry of Education, and DST, SERB, and DST itself, Technology Transfer Division. I wish to thank you for your kind attention. Yeah, I would like to.
So thank you very much, sir.
Yeah.
Thank you, sir, Srivatsa sir, for the extraordinary presentation today.
Yeah, I can see a couple of questions. If you wish, I would like to answer them.
Yeah, I request the participants to pose some questions. If you have any questions, please.
Yeah, so there is a question by Shivaji Chipuru. And the question is that they have worked on one-dimensional photonic crystal design using COMSOL. That's very good. Plasma material is the slots of dielectric material to achieve different EM polarization. How far is it feasible to create the plasma material? Let me tell you that there is a difference between plasmon and plasma. Okay, first of all, one has to understand this. Plasmons are excitations on metal surface. It has nothing to do with plasma. This term is synonymous to plasma because there are large number of charges involved. Okay, when I'm talking about charges in, that's why we are talking about free electrons in metals. The metals, I'm not talking about any metal. I'm not talking about iron. I'm talking about silver or gold, which has large number of free metals, large number of free electrons. Sorry, large number of free electrons, and that's why we call it plasmon. So it is not plasma. Okay, it is synonymous to plasma, but these excitations are purely on metals. Okay, so you don't need large temperatures at all. It is can be achieved at room temperature, and you can use simple light. You take, let us say, for example, in this bottle, I don't know, you cannot see this bottle somehow. You take a glass, because of this virtual background, I think, one moment.
Yes, sir.
So I don't take virtual background. I think that will be better. Okay, I think it's okay now. Yeah. So if you take, let us say, for example, this bottle, and you fill it with a colloidal solution of silver or gold, you simply shine light from this side, you can excite surface plasmon. I showed you different colors of nanoparticles. This is because of plasmon. So you don't need high temperature. Which software used to simulate plasmonic models in novel quantum structures? Of course, quantum structures is bit challenging. People are not using quantum, but they are using actually MATLAB or COMSOL to see the field profiles, and you can use a Python also. Python is free, for example. You can use Python. COMSOL is not free. Okay, so you can use these softwares to simulate plasmonic models. Okay, for quantum structures, of course, you have to do some analytical calculations, because you have to define the Hamiltonians. You have to you want to see how the transitions are taking place, so you have to calculate the transition. You have to take care of time dependent and time dependent perturbation theory. Perturbation theories to estimate the transition probabilities and all those things. Okay, so that is one thing. Yeah.
One more question from.
Yeah, there is no further question.
Which software used to simulate plasmonic models in novel quantum structures?
Yeah, so I have answered this. The software which we are using in our lab is MATLAB and COMSOL. I told you that you can use Python. Python is free, and there is another one which is Octave. This is also free. You can use Octave, okay, to simulate these structures. So these are free softwares. If someone doesn't have that much access or too money to use, one can use Python or this thing. Then there are other ones also for field profiles. Also recently there is another one, MEEP from I think from MIT. So there are other things also, free sources available. One can use it for this kind of applications. Yeah. Oh, there are other ones also. I see two more chats. I don't know. Okay.
Any questions from any other participants?
Sir.
So I request all the participants to switch on the camera for a second. I request all the participants to switch on the camera. I request everybody to switch on the camera for a few seconds.
I don't know. There is no less light at my. Now only I realize that there is no light on my face.
No, it's good, sir. It's good. Fine, sir.
Should be okay.
Sir. Yes, sir. Yes, am I audible, sir?
Yes, you are.
Sir, the session was very interactive, sir. I am counting that how many subjects are covered, starting from electromagnetic, optics, then machine learning, MEMS, micro and nanotechnology. So my question is, sir, is there any change in the material properties of the metal which people are utilizing in the phenomena of plasmonics at the nanostructure level?
Well, when you see the oscillation,
is there any
oscillations, something which is very interesting. So when you create a thin film from bulk, the number of free electrons and the surface increases.
Yes, sir.
Yeah. So you are increasing when you are
Yes,
making
sir.
a thin film, which is like few nanometers, only 50 nanometers or so. Basically, you are increasing the number of free electrons. So the surface plasmon excitation becomes very prominent. So in that case, the dielectric function changes a little bit. It is size dependent. No, if you take, let us say, for example, a bulk piece of any metal, and you make a thin film or thin nanoparticle, the dielectric property will change. In optics, in all these simulations, what you are using? Only the refractive index. So the refractive index changes. That you have to take care of.
Okay, sir. Okay, that's fine, sir. Fine. Thank you, sir. Thank you. Any other question, please?
Any questions?
Okay, no question.
Oh, if someone wants to take plasmons as a research topic.
HOD, sir, please.
There is
Any
another
questions
question
from anybody?
There is another question, just a minute. So if someone wants to take plasmons as a research topic, I think the best thing is to start with his propagating surface plasmons. Okay, you simply take a n layer model, let us say 3 layers, prism, metal, and then analyte. Or then you can add another layer or another layer, and you solve for the matrix equations. So it is given in very basic papers of Professor B.D. Gupta. In my group also, there are lots of papers available on this. Lots of people are using it for biosensing applications or sensing applications. So you solve for the reflectance, and then you can use it for sensing application. That is the starting point. Okay. Propagating surface plasmons. Yeah.
Hello, sir.
Yeah, Sultan.
Sir, as you mentioned, the materials are negative refractive index. Can you name some so that we can use for some other applications of plasmonics?
Yeah, there are other applications.
Hello?
I'm not saying the material has negative refractive index. I'm saying the real part of the dielectric function is negative. Okay. The real part of the dielectric function is negative. See, if the refractive index becomes negative, then there is no problem, So it will it doesn't follow the Snell's law. You can see that it will go like that. That's how people were doing this metamaterial thing. So
yes, sir, metamaterial. That is why I asked.
Yeah, so it's not the real part of the dielectric function is negative. That is available with metals, but the mu is not negative. Okay, so mu, people make surfaces and structures, engineer the material in such a way that mu also shows a negative kind of thing, but it is not actually negative. Now, other applications are like, sensors is one of the applications. You can make a polarizer because, it is showing transmission for TM, but not for TE. And then you can make a filter. You can change different wavelengths and you can select that which wavelength passes through, which wavelength stops. You can make a modulator. The field becomes enhanced, so you can place it in place near the solar cells. So solar cells also absorb more light. So then you can make it detectors. So there are different kinds of applications also. Okay. Cancer therapy, because people have used it for skin cancer. Let us say for breast cancer, you inject these nanoparticles in the breast, in the upper skin, and you shine light. Okay, so what will happen? It will create local heating, and that local heating will kill the cancer cells. So that also people have used for therapeutics also. So there are different kinds of applications. Yeah.
Thank you, sir. Thank you so much.
Yeah. There is one more thing. These thin films of silver are, silver and gold, they are antibacterial. So people use this in sweets. That people think that they are decorating the sweets, but actually it's not decorating. Our ancestors were very thoughtful. So it is actually not letting bacteria grow there. Okay, so these are other kind of applications. That is more like chemistry and biology part. It has nothing to do with plasmons anyway.
Yes, sir. Traditional knowledge, sir. Grassroots knowledge.
Yes. See how beneficial it is. You put silver or gold and it is the sweet stays for
See
long
the
time.
magic. Okay, sir.
Yeah.
Any more, any participants? Or else, I'll close the session.
There
Anybody?
is another question like quantitative sensors, other quantitative sensors. Yeah, of course, there are quantitative sensors. You know, you go for your pathology report of your blood. You will have, what are the lipid profile. They give some numbers: hemoglobin, bilirubin, calcium, potassium, all these ions. So these are all quantitative sensors. Okay, these are all quantitative. Air quality index, for example, in Delhi they have lots of pollution. There is air quality index. This is quantitative. Then in water also, you feel the TDS, for example. This is quantitative sensor. So these are all quantitative sensors. Okay. Yeah. I think we should end this. Yeah. If you have any further questions, probably you can put your question to the organizers. And I can send the answer to them.
Sure,
Okay.
sure.
Okay.
So thank you very much, sir. From the Department of ECE, NSRIT, we personally thank Dr. Sachin Kumar Srivastava, sir, Assistant Professor, IIT Roorkee, who has given extraordinary lecture on plasmonics, starting from fundamentals to the applications, with even including machine learning, everything. So very much thankful to you, sir, on behalf of the entire team of this FDP and from the Department of ECE. So we have a lot of questions are also discussed in this session. It's an interactive session and useful for the people over here. And in future also, I request you to be the part of some technical sessions from our side, sir. This is from a request from our side. And, now the feedback link will be shared here.
Yeah, sure. If everything permits, schedule, then it's okay.
Definitely. Thank you, sir. Thank you.
Yeah.
If possible,
Okay,
we'll call you
so
here
I
for
think
offline, sir.
thank you all for being a nice audience and quite interactive also. And I want to thank the organizers again, and I congratulate them for making this. I see a good participation, so it's a good one. And congratulate especially Virendra Singh ji to
Thank you, sir. Thank you very much.
one. Yeah, thank you.
Thank you.
I
Namaste.
would like to leave now. Yeah.
Yeah, thank you very much, sir. Once
Yeah.
again,
Is that okay?
thank you, sir. Thank you, sir.
Ah,
Thank
sir.
you very much. Yes.
Okay. Okay.
I request the participants to stay back for a while. Thank you very much.
Fill
Sir.
the Google form.
Thank you, Sachin ji. Thank you, sir. And I request the participants, the feedback link is already shared in the chat box. Please fill it. So please fill the feedback form before leaving. Once the session is closed, the feedback link will not be available. Please fill the feedback link for this session. So, and the second session of day 2 will start at 1:30 sharp. So, Dr. Nella Anvesh Kumar from VIT Bhopal will talk about directional ultra wideband and terahertz antenna technology for an hour. So, I request the participant to be available during 1:30 to 2:30, and session 3 from 2:30 to 3:30. Dr. Sripad Raja is a product manager, Intelligence India. So it's going to talk about MEMS devices, simulating of various MEMS devices from 2:30 to 3:30. And session 4 will start at 3:30 to 4:30. Dr. Abhay Sachdev is from the DRDO, CSIO, Chandigarh, who will talk about prospects and applications of nanomedicine. So this is the day 2 schedule completely. So I request all the participants to please fill the feedback link before leaving. Thank you. Thank you for the session 1.